So this was energy is fluid coming at point A. And this was energy is pump, that energy added to the fluid by the pump. At point B, energy remaining in the fluid. This mass is the loss in the pipe between point A and B. Similarly, in the next slide, I just put turbine and the pump. Okay, it's showing this is the energy remain. When fluid leaving point B, this much energy remain at point B. And turbine is this much energy absorbed by the turbine. And turbine absorb this much, but he is not able to leave all the energy from the fluid. So there is some loss. This is the loss. And at point A, this much energy in the fluid is heading to the point B. And this mass is the frictional loss. Okay, I just edit it. I think it was needed. Now, I summarize all the formula over here. What is the power of pump or turbine? How we can figure out? Rho G QH. We will discuss it in both cases. If you check the unit, rho G Q turbine, you see it coming joule per second. That means watt. Rho kg meter cube, G meter second square, Q meter cube per second, M equal to meter. Then this meter will be out, and you see kg meter second square equal to Newton. So Newton, then this meter second, Newton meter per second, Newton meter equal to joule. So ultimately is coming joule per second. That means watt. Okay. And this is the efficiency of the pump. This is the formula for efficiency of the turbine. Then how will figure out the frictional loss? By this formula. That's Weisbach's equation. Where F is the friction factor. If flow is laminar, then you can figure out directly the formula 64 by Reynolds number. But flow is turbulent, then you need to use the bigger equation, or you need to use the Modichart. Or if you use the Modichart, you can figure out both flow, laminar and also for turbulent. And this is the pressure drop. I will get the pressure drop between 2 points. If you know the frictional loss between 2 points A and B, say A is equal to 4 meters, HLF, we can easily figure out the pressure drop, because always use this formula, pressure equal to H rho G. So frictional loss, you are getting HLF, then that means pressure drop between 2 points, delta P will be frictional head loss, HLF, then you multiply by rho by G. Okay. That I put right over here. Delta P equal to rho G into HLF. This is continuity equation, that Q equal to area into velocity. Okay, now we'll solve this equation. I'm sorry, problem. Okay. You see that it's saying water flowing at a rate 15 meter cube per second. So obviously this value is given you the Q meter cube per second through a pipe system as shown figure below. Find power requirement by the pump. What type of pump you need, that you need to figure out. Assume frictional head loss in the pipe. Value of HLF is given 3.22 meter. Say, for example, You have a water tank, underground water tank right over here. You have a pump. You have a building 10-story height. Then you need to figure out what capacity of pump you need. Okay. So we just look to the data, what is given. This see right over here, diameter of the pipe is given. And the outlet diameter pipe is given. Pump is right over here. Then you see there is manometer attached at point 1 and point 2. And due to the point 1, pressure is less, point 2 pressure is high. So this is going down, going up. Okay. So what happened right over here? There is a manometric deflection, 3 meters. So from the manometric deflection, you can figure out the pressure difference between point 1 and point 2. Or you can figure out the pressure at point 1 and point 2. If you make a line right through right over here, then from point 2 is coming right over here, you get the pressure over here. Pressure, say at this point, will be equal to P2 plus this much height. It's coming down plus. Similarly, this side, you get P1 plus coming down how much height? It's coming down through this much height, including this much height of the water and this much height of the manometric fluid. That is given. And you see, Q is given. And diameter of the pipe both sides is given. So you can figure out velocity at point 2. How? QI. You can figure out velocity right over here. QI. So if we apply Bernoulli's equation between these 2 points, then what is getting right over here? At point 1, fluid have this much energy. This much energy. With this much energy, he is heading from the point 1. Then he is entering in the pump. That means pump is giving him energy. So this much energy giving the pump. With this much energy, he is heading toward point 2. So in the point 2, before he going point 2, this much energy is lost by friction. That we already have it already given 3.22 meter. And at point 2, fluid has this much energy. And you see right over here, datum is given, reference line. So from that reference line, what will be height of the point 1? 0. That means Z1 height is 0. What will be the height of point 2 if I apply Bernoulli's equation between point 1 and 2? So height from here to here, that will be Z2. Beyond V2, we can figure out, right? But we need to figure out P1, P2. So what is saying? Figure out the power requirement by the pump. What is pump power? Pump power P equal to rho G into Q. Q already given. Rho, we know, density of the water. But we need to calculate the H pump, head of the pump. So how we get the head of the pump? So from this equation, in the bottom equation, you need to figure out the head of the pump. So you see H pump, you need to figure out. Right over at V1 we know, Z1 we know, P1 we don't know. HLF we know, V2 we know, Z2 we know, but P2 we don't know. So there's some relationship between the P1 and P2 that need to figure out from the manometry. Okay. So let's see we can solve it easily. So math file. Okay. So first you have to look that which value is given. Okay, so you say water flowing in pipe. So rho equal to 1000 kg meter cube. And manometric fluid is mercury. So you put mercury. You can directly put density of the mercury is 13.56 into 1000. You can easily put density of the mercury. But what I did, I put the specific gravity of the mercury. What is the specific gravity? Specific gravity equal to density of the fluid divided by density of the water. That is called specific gravity. So top and bottom, if we multiply by G, then what are we getting? Gamma F by gamma W. So you just remember specific gravity of mercury 13.56. Normally, data of the mercury, then data of water, and also data of air will not given in the problem. As a mechanical student and student of fluid mechanics course, need to remember. I already mentioned it before. I think you need to remember density of water. You need to remember density of air. You need to remember density of mercury. Okay. Then also need to remember the viscosity of water, also for air and for mercury. So this data will not be given in the problem. Okay. So it's just saying the mercury in the manometric tube. So you know the specific gravity. So rho m will be 13.56 into rho w. Then you figure out the density of the mercury. Now, deflection in the mercury already given in the problem. 3 is equal to 3 meter. Now, diameter of the pipe. 1 second. If I copy, let me easy. So deflection in the manometer 3 meter. Diameter of the pipe D1 230 millimeter. So it convert in meter. At 280 millimeter, that's the point divided by 1000, 0.18 meter. Flow rate Q is given in the problem. Frictional head loss is given HL to the 0.3, 3.22 meter. Power of the pump that you need to figure out. Power of the pump equal to rho G QH pump. That is called power of the pump that you need to figure out. Then now how we figure out? We can apply multiplication between 0.1 and 0.2. So if we apply multiplication at 0.1, what are you getting in the left side? You are getting P1 by gamma. B1 squared by 2G plus Z1 plus H pump equal to P2 by gamma, B2 squared by 2G, Z2 plus HL. Now we try to figure out all the data. You see, that is our objective. We need to figure out the power of the pump. Rho we already know. G value we know. Q already given, but H pump is not given. That we need to figure out. So Z1 from this is 0.1 from datum line, Z1 will be 0, right? So we put right over here Z1 0. Z2 height from here to here is not given, but it says Z2. So we put just Z2 equal to Z2. V1, V2 we don't know. P1, P2 we don't know. So from here, we figure out the H pump. All the term you take right side and this is the equation for H pump. Now, we need to figure out, you see right over here, what we have? P2 minus P1 divided by gamma W, right? So that means we have P2, right, that left side, right side, P2 minus P1 divided by gamma dot W. If you figure out this value, then you just put it over there because SLF we know. V1 we can figure out, QIA1, V2, QIA2. So this term we need to figure out. Okay. So what we did, we apply manometry between 2 points. 1 point right over here and right over here. Remember, at both points, pressure will be same. So left side, we try to figure out the pressure from point 1. So left side will be P1, then you coming down all the way right over here. So if you coming down from the point 1, you have to travel from here to here. That means P1 plus, what is that height? Z. And fluid is water, right? So Z rho W into G. Then you coming down from here to here, to come over here. What is the height? H, right? They will say H equal to 3 meters. And density of the fluid, rho M, manometric fluid. So H rho M G, that will be pressure right over here, equal to this point, the same, right? So figure out pressure at this point from point 2. So for point 2, what is the height? P2 plus all the way coming from here to here. And all the fluid is water. So Z2 plus, you get this Z2 plus this Z plus this H. So Z2 plus Z plus H rho W Z. Now you just simplify. And after you simplify, you see 2 terms will be out. This term and this term will be out. And you will have Z2 and you will have H. Now we need to figure out this value. P2 minus P1 divided by gamma W. So you just simplify this equation. If you simplify this equation, these 2 terms will be out. This term Z gamma W, Z gamma W. Then both sides, you divided by gamma W. This gamma W. So finally you get this one. H, this is out already. H gamma M by gamma W. Over here will be only gamma W will be out, only Z2. Z2, then gamma W will be out, only H. Okay. Now this value, equation 2, is substitute in equation 1. So you put in equation 1, you get this one. Now this one you see HLF we know. What is the unknown only? Unknown is V2 and V1. So you figure out the area at point 1, this mass 5 by 4 D1 square. Area at point 2, then you figure out V1. V1 equal to QY A1. So this is V1. V2 equal to QY A2. This is V2. Now you are getting gamma. Figure out the gamma M and gamma. Gamma equal to rho G. You figure out the gamma over here. Okay. Then put everything in the equation. You get head of the pump 42 meters. Now what is the power of the pump? H rho G Q. So H is the head of the pump. This is the Q already given in the problem. Rho you already know. So you get this mass watt. then we convert in the kilowatt. Okay. Any questions? Any questions?
No, sir.
No?
No, sir.
Okay. Let's go through the next problem. Okay. Are you hear me? Hello.
Yes, sir.
You can hear me?
Yes, sir.
Yes, sir.
Okay. Good. But is you are completely silent, then sometime I think I might got disconnected. Okay. So let's solve this problem. You see in the left side, it's showing water. And from this level, height of water is 70 meters. 70 meters means how many feet? You multiply almost 3, more than 3. So 3 into 70, 210 feet. Huge energy. 210 feet to only one-story building, right? How got that much height of the water? Say if you make a dam in a river, then before the dam, your water height will gradually increase, right? Say the river coming, in that river you put a dam. Then at the front side, water height gradually will be increased. Then you make a little channel, then water will be coming high speed, you put a turbine will rotate, you will get the energy. So like Kaptai hydraulic power plant. Okay. So right over here, they are saying showing the height of the water is 70 meters. Then from here, they put a turbine. From the turbine, water is, it can go straight horizontal. Instead of horizontal, they put a nozzle and water is going at an angle 45 degrees from the turbine. And they mention some points. They're saying this is point 1, this is turbine point 2, this is point 3. Point 3 actually diameter of the nozzle. We see they given, they don't say nozzle, but from the figure you see kind of nozzle. And this is the diameter of nozzle, 50 millimeter. And they're giving one more point, point 4. It's saying at point 4, they're showing velocity, you see 15 meters per second. Now, what you need to figure out? It's a water flowing from a turbine as shown in the figure below. Find the power developed by the turbine. That means how much power output out from the turbine, that you need to figure out. Is given turbine efficiency is 80%. And frictional loss in the pipe from here to here. You don't know what is the how much distance from here to here, but that's why they're just giving you the loss. So this time you don't have to use the Darcy-Weisbach's equation, right? Because frictional head loss already given in the data. So they like to figure out, they like to know what will be the power output from the turbine. So if you apply Bernoulli's equation between point 1 and 3, you look point 1 and 3, what will be the velocity at this 2 point 1 and point 3. Point 3 obviously have some velocity, right? But point 1 velocity almost 0 because you are maintaining constant height. What will be pressure at point 1? Obviously atmospheric pressure. Point 3, water is just coming out through the nozzle. So obviously this is uh, atmospheric pressure. What will be Z1? Z1 will be 70 from this datum. You can consider datum anywhere, but I am considering this on my reference line. So Z1 will be 70 and Z3 will be 20 meter is already given. Now, what is the turbine efficiency? This is turbine efficiency equal to P output by rho GQ H turbine. Efficiency is given 80%. Rho of oil dealing with water, so you know density, G value you know, but Q and H turbine you don't know. So you need to figure out H turbine, you need to figure out Q. How will you figure out the Q? You see only diameter of the pipe is not given, but diameter of the nozzle is given 50 millimeter low, right? 5 centimeter only, about 3-4 inch. So from here, if you know the velocity at point, I can figure out the Q. How? That Q equal to area at point 3 into V3, velocity 3. So area you can figure out from here. Diameter is given 5 by 4 T square. But how you know the V3? Actually, right over here, you applying knowledge of your engineering mechanics. How? When fluid coming out through this nozzle along this direction, right? Then it has a certain angle. With the horizontal line, angle is 45. That means it has a two component, the velocity component. One is horizontal component, other one is vertical component. So the fluid coming over here for your horizontal component will be remain same, but vertical component will go down a little bit. Why? Because gravitational force working downward. When coming at point 4, horizontal component remains the same, but vertical component is 0 because G working downward. You know from your college that V square, if something moving upward direction, V square equal to U square minus 2GH, right? So height increasing gradually, this difference U square minus 2GH coming close to the 0, because right over here, upward velocity will be 0 at point 4. So point 4 upward velocity is 0. So horizontal component remains the same. Now, if you think that fluid particle if came in another point, say right over here, what happened? Your horizontal component still 15 meters per second, same. What is the downward component? Now it's free falling down from the roof, right? Over here velocity 0. That means working gravitational force downward. So what is the movement of the fluid particle? It will move along this direction. So gradually it will fall down in the ground. So you see this horizontal component of this force is not changing. So what is the value of this horizontal component force? If I say this is U and this is my V, so I can say that U equal to V cos 45 or cos theta, right? If this angle is theta. This horizontal component is not changing, it remains constant. So V cos theta equal to horizontal component, and this value is given at point 4. This is equal to 15. Cos theta, cos 45. You can have cos theta 1 by root over 2. Then from here you figure out the V at point 3. That means U equal to cos B3 into cos theta. equal to 15. From there, you figure out the B3. You have B3, now figure out the Q. Q equal to B3 into area A3. Okay. So let's go through the NathCAD file. Okay. So at first we need to write down that what data is given. So you write down density given, you draw the figure, then it's a density of the water is a water over here, 1000 kg per meter cube. Frictional head loss is given, it's a 5 meter, you write down. Turbine efficiency 80%, that means 0.8. Diameter of the nozzle equal to 50 millimeter, then it's a write down equal to 0.05 meter. Velocity B4 at 0.4, 15 meter per second. Inclination of the nozzle 45 degree. Then you need to figure out turbine power P out equal to how much, that you need to figure out. So if B3 is working along this direction, so it has two components, horizontal and vertical. So B3 into cos 45 will be equal to 15. That will be equal to B4. B3 into cos 45 will be equal to B4. So from there, you figure out the B3. B4 by cos 45, you get 21 meter per second. Now, you figure out the area of the nozzle, 5 by 4 dn square. Nozzle diameter is given. So you get the area. From the area, you figure out the Q. This is your Q. Now, you need to apply the Bernoulli's equation. So, Bernoulli's equation between point 1 and so at point 1, you are getting this one. P1 by gamma, B1 squared by 2G, Z1, then turbine coming over here, turbine absorb energy this much plus loss in the pipe, and with this much energy fluid is getting out from point 3. Now Z1 70 millimeter is given, B1 0. We assume that height is constant. That means this fluid particle right over here is not moving down. If he moving down, then height should not be constant, right? So this Z1 B1 equal to 0. P1 atmospheric pressure. Z3 is given 20 millimeter. B3 we already figure out is 21. P3 atmospheric pressure. All the data now we put over here. So this atmospheric pressure, this value will be out. B1 0, this will be 0. Z1 is given. So easily we can figure out the H turbine. So from here, we are getting H turbine equal to 22 meter. Now, what is the formula? Turbine equal to this formula, P out by rho G Q H turbine. So you see right over here, P out equal to efficiency into this mass. Efficiency equal to 0.8, right? H turbine we already figure out. So we are getting 72.07 kilo, not kilowatt, this one is watt. And I convert in horsepower is this much, but still you can figure out in terms of kilowatt. So if I change the unit, giving me in terms of kilowatt. Okay, very easy. So any questions? Any questions?
Sir, the value of HLF here.
HLF. HLF is already given in the problem. You see HLF equal to, did you see the
Meter.
PowerPoint, right?
Yes, sir.
HL is already given in the problem equal to 5 meter. But in the next chapter, we'll show you how you can figure out the value of HLF from Darcy Weis classification. Okay. But right now we are showing solving some problem that frictional loss already given. So you don't need to use it. Okay. Anyone? Any questions? No? You see at the top, frictional head loss, we already write down over here. Is equal to 5 meter is given. So any question?